Okay, we are at section 7.6, potential energy of a system. Let's share the PowerPoint, and we're going to talk about potential energy. Now, we previously talked about kinetic energy. Kinetic energy is equal to 1/2 mv squared. Um, Now, notice that if v is equal to 0, uh, then the kinetic energy is equal to 0. So kinetic energy is, as the name indicates, kinetic. Kinetic energy is the energy of motion, the energy of motion. If you have zero velocity, no motion, then you have no kinetic energy. Potential energy is the energy of position, whether that position comes from gravitational force or spring potential energy from the elongation or compression of a spring. It's the energy of uh, it's energy of position. So let's look here at this, uh, this this image here of a physics book being raised. The work done by the agent on the book Earth system is mg y final minus mg y initial. Well, what is mg? Mg is the force. It's the um, gravitational force, and y is just the distance. So it's a force times distance. You're doing work. So if you're raising the physics book up uh, from y initial to y final, you've done work, and the amount of work that you've done is mg y final minus mg y initial. So r is equal to y final minus y initial times the unit vector j, and that's in the j direction. So the work done on the book is the applied force times delta r. So that's the force is mg in the j direction, and that's y final minus y initial times j. So j dot j is equal to 1. So you end up with mg y final minus mg y initial. So the potential and the gravitational potential energy is mgy. Um, I don't know why I would put a delta y there, but it's the change in position. Okay, the work done is the change in the potential energy. Okay, gravitational potential energy depends only on the vertical height of an object above the surface of the Earth. So if we have a force, let's say we fire a cannon and a projectile, and it has both a um, x component and a y component. So the applied force times delta r. The applied force in gravitational potential energy is mgj dotted with the x final minus x initial uh, uh, time in the I vector plus y final minus y initial in the j vector in the um, vertical position, I be in the horizontal position, J be in the vertical position. Well, J dot I is equal to 0. So those terms will cancel out. And all you're left with is the mgy final minus mgy initial. So any motion horizontally does not add to the gravitational potential energy. It's only in the vertical position that you get gravitational potential energy. Okay, choose the correct answer. The gravitational potential energy of a system is always positive, is always negative, can be negative or positive. And it can be both negative or positive. The change in potential energy, uh, it can be negative. If you lower something, then gravity has done work and it's negative. If you do work on a book, it's positive. You've given it potential energy. Okay, elastic potential energy. Here we have a spring, and the x equals 0. We call that the quiescent point. If you move the mass and compress the spring by X. You move it a little bit more, you get X max as shown in C. The spring will push against the mass and give it a velocity. And once it fully extends, it's going to give it the maximum velocity. You can see that little red arrow is a little bit longer than the one at the bottom is a little bit longer than the one above it. So the work done is the change in the work is the is 1/2 kx squared. So the change in work is 1/2 kx final squared minus 1/2 kx initial squared. So the spring potential energy is equal to 1/2 kx squared. Assuming that the initial position is 0. So the work is the change in potential, the spring potential energy. Now, they have here the same graph, but here we have some energy diagrams on the energy bar graphs on the side. Before you compress the spring and before you move the block, there's no kinetic energy, there's no potential energy, and there's no total energy. But if you compress the spring, you've given it some potential energy, and the total energy is the same as the potential energy that you've supplied. You compress the spring more to the maximum amount, and then you have all elastic potential energy and the no kinetic energy. It's not moving, and so your total energy is the same as the potential energy. Now, after the block is released, the elastic potential energy decreases and the kinetic energy increases. And when you start having velocity, you get some kinetic energy. And once the spring is fully extended, it has released all of its potential energy and it has turned it into kinetic energy. But you can see at the point that we've reached X max, the total energy doesn't change. And we're going to do a little online experiment with Walter Fent spring energy. I showed this to you last Thursday when we were doing when we were talking about energy. Okay, let's. A ball is connected to a light spring suspended vertically, as shown in the figure. When pulled downward from its equilibrium position and released, the ball oscillates up and down. In the system of the ball, the spring, and the earth, what forms of energy are there during the motion? Well, as it's moving, if there is motion, it's certainly kinetic energy. And if the spring is being compressed or the spring is being elongated, there's elastic potential energy. And if the ball is moving up, there's gravitational potential energy. So the only one that has all of those is C, the kinetic energy, elastic potential energy, and gravitational potential energy. Okay, let's look at a ball is connected to a light spring. It's the same problem in the system of the ball and the spring. What forms of energy are there during the motion? The kinetic and elastic potential energy. Kinetic and elastic potential energy. In other words, if we're just looking at the spring, it's just kinetic and elastic potential energy. That's a little more related to the horizontal one because there is gravitational potential energy, but they're talking about the system of this ball and spring. Okay, the energy bar charts, I think this is really the same graph that they've shown you in a couple of slides ago. So I don't know that there's any reason to go through it again. you can see that the total potential energy doesn't change. And when we do that Walter Fent online experiment, I want you to notice the potential energy. Okay. All right. Conservative and non-conservative forces is the next section, 7.7, so we'll end right there.